In this video, we'll be looking at examples of geometric series, and we'll be applying the rules for convergencies of geometric series. So, in this particular example right here, the determination is, does this series converge or diverge? That's always going to be the question when we're looking at a series in most cases. So the question is does this series converge or diverge? And just by looking at it, I know that since this is 1.1, a number, to the power of k minus 1, this is in some form of a geometric series. So I'm going to go ahead and note that this is a geometric series. So just by looking at it, I know what kind of series it is. By knowing what kind of series it is, I know that I have a set of rules for when a geometric series will converge. And the rule is that a geometric series will converge when r is absolutely less than 1. Now, I'm using this absolute bar, and in the previous video we used this notation, but the notation is the same, okay? The statement is the same, the notation might be different. So I'm going to use this notation when I go ahead and determine whether or not a geometric series is convergent or not. So when I look at this series right here, because r is not less than 1, I can say that this series diverges. And why does it diverge? By geometric series with r greater than 1. So now it's important for us when we're doing these problems to clarify or at least identify what we're actually saying. I'm going to say, again, very clearly, this series diverges. This particular series that we're talking about diverges. And why does it diverge? Because it is a geometric series and the r value happens to be greater than 1. Let's look at the next example. The next example gives us k equals 0 to infinity of e to the power of negative k. Now, when working through this particular example, you might look at it and say, well, wait a second, this is a geometric series because it's e to the power of some form of k. And you might then also say that, well, the e is larger than 1. So therefore, this thing must be divergent. You will be tricked into understanding that or believing that because of that negative k. Be very careful. Make sure that, again, the form of a geometric series is the summation of some form of a, r to the power of n, or to the power of k. It's some form of this concept. The fact that this is negative flips that whole concept. We must actually evaluate that negative exponent. And if you recall, that negative exponent really then becomes the summation of k equals 0 to infinity of 1 over e. That whole thing is to the power of k. Technically, it's the e to the power of k, but I can go ahead and shift that power of k both onto the 1 and the e, and it's not going to change the ruling of that this thing being the same as this thing here. With that being said, as k goes to infinity, this is now a geometric series, and the statement is r absolutely less than 1? And the answer is yes. 1 over e is a fraction. It's an exponent, or sorry, it's a decimal value, but it's also a fraction. With a fraction such that it's less than 1, we can say that this thing is definitely guaranteed to be convergent. Now, here's the kicker of how this thing is actually going to work, however. I'm going to go ahead and utilize this information and plug it into the rule. The rule is, if this is true, I'm going to go ahead and put a check mark here, this is true, then my geometric series converges to a over 1 minus r. Now, in the previous video, when I was talking about a, I was talking about, well, what is the value that's in front of this? I wasn't necessarily saying that. I was saying, if I were to take my first value, in this case my k value is 0, and I plug that into this thing, and I evaluate that term is my a. It just so happens that when I plug in 0 this time, that 1 over e to the power of 0 is 1. So my a value happens to be 1. Because technically this is not a, it's a sub, and using a 1 is not good notation because that means I would be thinking of this as a sub 1. And this is the first term, but this is using k sub 0, or sorry, k equals 0. So this is technically a sub 0 of this particular sequence. So in this case, again, it's just important for us to note that when I'm looking for a in this geometric series formula, that I'm looking to plug this value in, and whatever I get back for this entirety of the function, that's my a. 1 minus, and then my r value I just have to determine is, well, what is it to the power of k? 1 over e is what's to the power of k, so I get this. Now, this is a valid answer, but I don't like the fractions of fractions. So we're going to go ahead and just multiply by the common denominator in the denominator. That's going to be multiplying top and bottom by e. That way that this top piece here becomes e, and this bottom piece, when distributed through, becomes e minus 1. And this is just a better looking form of an answer. So that is how you're going to utilize that formula of a over 1 minus r to show when a geometric series converges, what it actually converges to. Let's do this one more example. I'm going to start at k equals 2 this time, going to infinity. And the series will be 3 times negative 0.75 to the power of k. Now, when looking at this series, we can again, one more time, utilize the rules of the limit of partial sums. However, that seems like it's going to be a lot more work than it needed to be. What I can do, however, is I can look at this in the form that it is and say, hey, listen, this doesn't start at 1, nor does it start at 0, so technically I can't argue with these two examples that it's some kind of geometric series, but I can argue that it's a geometric series because it's something to the power of the indexing variable. Something to the power of the indexing variable. Something to the power of the indexing variable. And again, it could be k minus 1, it could be k plus 1. If it's negative k, we have to manipulate it so that it's just k in some form. So this right here very much shows me that I do have a geometric series. What you'll notice the difference in this case between the previous cases is that this does also have a number in front. So, the next question you want to ask yourself is, are absolutely less than 1? Well, this is a negative 0.75, so yes, it's absolutely less than 1. If I were to take the absolute value of that, I get less than 1, so I know I have a convergent geometric series. Okay, I know that I have a convergent geometric series. So with this series being convergent, I just got to figure out what it converges to. So I'm going to go ahead and say this. This series converges by geometric r absolutely less than 1, and it converges to. So that's the question. What does it converge to? Well, it's going to converge to a over 1 minus r. Now, like I said in this previous example up here, my a value isn't just this number 3. My a value is what happens when I plug in this k value. So this is going to be 3 times a negative 0.75 all to the power of, sorry, to negative 0.75 to the power of 2, divided by 1 minus, and my r value again is very clear, negative 0.75. So minus a negative 0.75. So we can clean this up a little bit, but if we were to do so, again, algebraically manipulate this, the bottom piece will be 1.75, the top will be negative 0.75 squared, and we'll go ahead and manipulate the fractions so that we don't have any more decimals, and we'll end up with something along the lines of 27 divided by 28. So, in this case, I can conclude that this series is a geometric series with r less than 1, and therefore will converge to that value. This one up here, same exact statement. This series converges because it's a geometric series with r absolutely less than 1, and it converges to that. Now, after we've done that, there is one more type of example that we might want to consider when looking at these types of geometric series. And that is, again, very similar to the 0.9 repeating that we did prior. So we're going to look at 1.035 repeating. The question is what does this equal to in fractional form? Now, yeah, sure, you could type this into a calculator, go ahead and hit that math enter button, force it into a fraction, and hope to God that you've typed in enough 3 5s over and over and over again to get the exact actual fraction. There's a better way to do this in a more consistent path to show that it is definitively going to be that value. So the first thing we're going to do is that we're going to note that this thing is equal to 1.035353535 and so on and so forth. I'm also going to then make note that this is 1 point, heck, you know what, let's just leave it as 1. 1 plus, and I'm going to do 0.035 plus 0.00035 plus 0.0000035. And you'll notice that if I start smashing these things back together, I will get this number up here. I could do one more, but I don't think it's necessary for us to show that anymore. This is then also going to be equal to 1 plus, and now you'll notice here that it's important to register that this 1 is not part of the repeating decimal, so this 1 might not actually be part of my series when I end up creating it. So looking at all this, let's talk about how can I turn these three things into basically the same starting term. So 0.035 is my basic same starting term. I could use 3.5, I could change it to be 35, I'm going to go ahead and just leave it at that decimal for now. I'm going to move this decimal place 2 units, which means I'm going to change this to be 0.035, but isn't that really just multiplied by 1/10 to the power of 2? The same can be said for this one. I'm going to move it twice and then twice more. So I'm going to get 0.035 as a starting term and have 1/10 to the power of, instead of 2, to the power of 4. So if this is the case, then I would argue that I should be able to plug this stuff into a series. So 1 plus, and I'm going to go ahead and do a summation. Now, the fact that this is a 2 and this is a 4 might throw us off in terms of the way that we'd really want to set it up. Well, we could just change these things to be 1 over 100, and that's then to the power of 1. And I could change this to be 1 over 100, and that's then to the power of 2. And then it follows a logical pattern of if I use k equals 1 to infinity, then I'm going to have 0.035, and this is where developing your sequences based on patterns comes into play. This is in every single one. I'm going to have 1 over 100 in every single one. In this one it's 1, in this one it's 2, in this one it's supposed to be a power of 0. So if I start at k equals 1, this should be k minus 1 to start, and then it's going to build the rest of this pattern. So this is actually what that thing right there really looks like in series form. And I can very clearly then say, hey, wait a second. This is a geometric series with r being equal to 1 over 100, which is less than 1 absolutely. And therefore, this series right here, will converge to A. If I plug in 1, my A value is actually this 0.035. And again, I created this in such a way so that that did happen this time, divided by 1 minus my R, which is 1 over 100. Hence, if I were to manipulate this thing right here, and then add 1 to it, again, don't forget that this thing is equal to this, so this overall number is 1 plus this 0.35 divided by all this stuff, which is actually going to be, I think, 35 over 990, which if I add these values together, I'll end up with 205 over 198. And this is the fraction that this decimal is actually equal to. Again, this is utilizing geometric series in its most appropriate form. It's important to remember that any geometric series will converge if r is absolutely less than 1 and will diverge otherwise.